Section 13.1 is vector fields, and we'll look at vector fields in 2 dimensions and in 3 dimensions. So we'll let D be a set in R2, the plane. So D is some planar region in our Cartesian plane. A vector field on R2 is a function f that assigns to each point x, y, and D a 2-dimensional vector. Call it f of x, y. So for each point, each 2-dimensional point, we have a 2-dimensional vector at that point, whose initial point is at that point. So to see one of these simply, we have a vector field on R2. It's defined by f of x, y equals negative y comma x. So it's a function of position x, y in the plane, and the vector at that position is the vector negative y comma x. Describe f of x, or f, by sketching some of the vectors of f of x, y. Well, off to the side, we made a table, sort of an arbitrary selection of points x, y in the R2 plane, in the plane R2. And, well, here's f of x, y for each of these. All that really f does is permute y and x's position, and it puts a minus sign in front of the y coordinate, or whatever the y value was. So we come up with these vectors for each of these points, vector positioned at this point. So the vector will have terminal point at the given point x, y, and then of course its direction and magnitude will be sketched accordingly. So for this point, with terminal point -1, -1, we're actually here in the picture. -1, -1 is down here in quadrant 3. And the vector at this position is 1, -1. So this is the vector with components 1, -1. Okay, if we continue that process, let's see another one. -1, 0 has vectors 0, -1. So position -1, 0, which is here. The vector that's in this position, this initial point here, is 0, -1, and that's this vector that's pointing downward. We continue down the line for each point, building up the vector that should be at that point. 0, -1 is here, and it has vector 1, 0, the vector that's drawn. And of course, there are many more we could do. There are really essentially infinitely many vectors we could draw into this vector field, but that wouldn't be useful to try to do or to have as a picture. So we want to be somewhat selective and sketch as many as we can just to get an idea of what this vector field looks like. It looks like there's somewhat of a spiral to some degree. Looks like that if a particle were to start here, it would travel along this vector, then it would travel along this vector, then this vector, and potentially another one that looks like this, and we would keep working our way outward. But maybe seeing a larger or a more full picture of that might convince us of this situation. So Geogebra is a really good tool for sketching vector fields, particularly in the plane. They're nice and easy to see. So you can see what I used in my parameter window for Geogebra. I set my x component to be -y, and I set my y component to be +x. Now it does say v sub x of xy. What that's asking for is the vector in the x direction at the position xy. It's not a partial derivative like some might interpret it. Okay, some things that are set here. Min and max for the windows, so that's how much of the field of the plane we want to see. And a little lower is the vector lengths, right? Where we seem to be limiting the vector lengths by some proportionality. And what that does is it makes our picture seem a little bit more viewable. On the previous page, in the hand-drawn vectors, we had everything true to scale in terms of vector length, and it was going to get a little bit crowded if we were going to draw any more vectors in there. On the other hand, these things can be adjusted to make the vectors a little longer if we choose, but I think we see that this picture is pretty useful off to the right here. Notice that the closer we get to the origin, the smaller these vectors seem to be, right? They seem to have magnitude less and less. The length of a vector on this as drawn in a vector field will indicate its magnitude. I think the largest magnitude we see is a vector like this, which is the furthest from the origin in this graph. Okay, and it does look like, you know, let's track the path of something in this plane. So if we started at arbitrarily this vector, maybe we'd arrive at this vector, and then we would arrive at this vector, then here, then here. And I'm just sketching roughly where this path might take us. It does look like we might be sort of spiraling outward further away from the origin. And that's just a thought for later on. What we're going to see is paths in vector fields. So in other words, maybe a current stream or something like that that is pushed by this vector field, or a trajectory that a force field acts on a particle with. So let's consider a vector field in three-dimensional space. It's essentially just defined the same way. If E is a subset of R3, a vector field on R3 is a function f that assigns for each point x, y, z a three-dimensional vector f of x, y, z. So these vector fields are essentially just like transformations, right? They take a point in 3 space x, y, z, and they give us a three-dimensional coordinate or three-dimensional vector f of x, y, z. So we're mapping from R3 to R3. Now, for the function we're given here, the vector field we're given here, it's f of x, y. We're actually missing a dependency on z in there, even though z doesn't explicitly show up on the right. This function treats z as a constant over here. But there's our R3 to R3 vector field. It's 0, 0, y. So the only thing that really matters in terms of forming these vectors is what the y component is, and the y component is actually placed in the z position, right? The y variable from this argument is just the value that the z component of the vector takes here, and everything else is 0. So that being the case, and we could form some vectors arbitrarily off to the side to get an idea of what this looks like. But let's look at maybe the vector 1, 0, let's see, 0, 1, 0. So my coordinate axes have been rotated from each other, but 0, 1, 0 is the point right here, 0, 1, 0. Positive on the y-axis coming out of the page towards us, and no, it doesn't move at all from the xz plane, or yes, it doesn't move at all from the xz plane. It's centered on the xz plane. So position 1 above the xz plane, but y equals 1. Now z has a value of 1 for this vector. 0, 0, 1 is what our vector will be since y is positive 1. So that forms the vector 0, 0, 1. Now at the position 0, 0, 2, or 0, 2, 0. So 0, 2, 0 is our input vector, and that comes out as 0, 0, 2 once we apply the function to it, and we get a vector of length 2 pointing in the positive z direction. Similarly for 0, 3, 0, we're here, and that vector is 0, 0, 3. We see that as we move further out along this y-axis, we'd have larger and larger vectors. On the other hand, going back the other way, at 0, negative 1, 0, we have the vector 0, 0, negative 1. Stepping back again, at 0, negative 2, 0, we have the vector 0, 0, negative 2. Now, what happens along the x-axis? Well, if we see here, nothing really changes if we vary x. So each of these vectors looks the same as if we were to extend along the x-axis and have a look. And that's, in fact, more or less how I've tried to draw this in the background here. Each of these vectors here are the same for any given x value. They're all along the line y equals negative 1, or along the plane y equals negative 1, we might consider. And similarly for y equals -2, we get another set of 4 vectors, or even more if we were to continue, with a length of -2 pointing in the negative z direction. So the short description of this is down below. The vectors increase in magnitude as the distance from y equals 0 increases. And the vectors corresponding to y greater than 0 point upward, as we see in the foreground, and those corresponding to y less than 0 point downward, as we see in the background. So a GeoGebra representation of this, using the 3D vector function or vector field tool. First component 0, second component 0, third component is y. And this gives us a pretty decent picture of what's going on. It's a little bit hard to see maybe exactly where everything is in this picture, but this is the positive x-axis this way. This is the positive y-axis this way in the background, the negative y-axis in the foreground. If we see in the foreground that our vectors are pointing downward, all of these vectors are pointing downward. So that's consistent with y being negative. And in the background, we see that our vectors are pointing upward. And that's consistent with y being positive. 0, 0, y is each vector at each position. Now, other things we might be able to tell is that we have larger magnitudes the further we are along this y-axis away from the origin in either direction. It's harder to see that for the positive y values, but maybe for the negative y values we can start to pick that out. It's somewhat difficult to tell, but a close inspection of it might point it out. The reader's encouraged to use GeoGebra to have a look at these things. Zoom in and see what you can find in these tools. Of course, in GeoGebra, you can actually rotate this plot and have a better idea of what this thing actually looks like. So gradient fields. If f is a scalar function of two variables whose partial derivatives exist, the gradient of f is given by this, as usual. In this situation, we see that gradient of f is really a vector field on R2. It's called a gradient vector field. Okay, so we can use a scalar function. In other words, a function f from f of xy being equal to a single value, single function of x and y. And we can take its gradient and form a vector field based on that. It will be, in this case, a map from xy, R2, into an I component and a j component. That's also R2. So we see how any gradient of a scalar function could be a vector field. So let's find the gradient vector field of f of xy equals x e to the xy. So taking the gradient of this function first, partial derivative of x with respect to e to the x, or partial derivative of this function with respect to x. Derivative of x times the second function is 1 times e to the xy, and then plus x times the derivative of e to the xy. The derivative of e to the xy is e to the xy times the constant y, which is the coefficient of x in this partial derivative. That gives this portion right here. So there's a complete product rule for the partial derivative with respect to x. Now the partial derivative with respect to y. Everything is constant except for that y in the exponent. So that's x times e to the xy times x for the coefficient of y, this partial derivative. And we have x squared e to the xy. Everything has a factor of e to the xy in it, so we can factor that out of the vector and we'll put our answer in this form. So there's our gradient vector field from this given function f. Of course, drawing that one might be a little bit complicated, but so we'll avoid that in most cases. Now, last thing to mention is that a vector field f is called a conservative vector field if it's the gradient of some scalar function. In other words, there exists some scalar function f such that f is equal to the gradient of f. And in that case, we'll call little f the potential function of f. Okay, so it's the function whose gradient is the vector field is the potential function. So one last example, and this involves gravitation. So the force of gravity between two masses M being a smaller mass and M a larger mass. It's not necessarily the case, but it's one way to think about it. M is a planet, and capital M would be maybe the mass of a planet. Lowercase m would be the mass of some particle near the planet or on the planet. So the force of gravity between these two masses is given in terms of its magnitude as m times the gravitational constant g over r squared, where r is the distance between these two masses. So what we'll do is place that larger mass m at the origin in R3, and what we're asked to do is to determine the force of gravity F acting between the two masses as a vector function, and also in terms of its expanded components x, y, and z. Okay, so if capital M, the larger mass, is at the origin, and M is at the position x vector x, y, z, so these components x, y, z, then we'll have the direction of the force pointing towards the origin. So the unit vector in the direction of the origin is negative x over magnitude of x. So think about that. If you give yourself maybe any old vector x and consider if it's going to point back at the origin, what you need to do in order to find a unit vector that points back towards the origin from that position. So I think a quick calculation with a couple numbers might help confirm the reader of that. But anyway, that's the case here. So the vector function, or the vector expression of f, is, well, one step in between. We multiply it by the unit vector, and we arrive at this expression off to the right. Negative m, capital Mg, all divided by the magnitude of x cubed times the vector x. Okay, in terms of its components, that's quite a bit more interesting, just to see what's going on in the details. Well, its components are x, y, and z, so those will be the three spaces, and the magnitude of x is x squared plus y squared plus z squared, all to the power of 1/2, and that's cubed, so that'll be to the power of 3/2, and when we expand this, we find the following notation, or the following components for f. And notice that the x, y, and z components have each of x, y, and z in them. Okay, so that's the component form of this vector, or the expanded components of the vector. Now, if we inspect this, really think about it, we realize that each of these functions is the partial derivative with respect to x, y, and z from left to right of a function lowercase f is equal to this. Okay, with a little practice or a little bit of thought, this should be pretty easy to see, but it's certainly easy to confirm. Right, so I'll let the reader do this as an exercise. Confirm that the gradient of this function is equal to this vector field for capital F that we have up here for the vector field of gravitation. Okay, and that being the case, there exists a function f such that gradient of f is equal to the vector field f. So f then is a conservative vector field. It's the gradient of a scalar function f. So it turns out that gravitation, the vector field induced by gravitation, is a conservative vector field. That's one small use of it. Of course, electric fields are very similar, and the equation for electric fields is very similar to that. And we can do something completely similar with charge little q and charge larger q, and the vector fields induced by those attractions or repulsions. So that's it for 13.1. It's a pretty simple section, just essentially definitions and being able to sort of have a notion for what vector fields look like in terms of their graphs, or at least how to set up some basic calculations for vectors in a vector field. And much of what we do in chapter 13 will depend on just some small knowledge of how these vector fields are set up and what they look like.